Good morning students. In the previous video on electric potential and capacitance part 2, we have seen what can be the potential at a point in the presence of many charges or due to a group of charge. Now in this new video we are going to discuss about what can be the potential at a point in the presence of a dipole. So as we have discussed in the previous chapter, electric dipole is a system of two equal and opposite charges separated by a small distance. So we can find electric potential due to a dipole in two positions. What can be the value of electric potential on the axial point of a dipole? So what is axial point? Axial point is a point lying on the axis of the dipole. Axis of the dipole is a line joining two charges of the dipole. Here point Q is axial point of the dipole. The distance of point Q from center of the dipole is small r. So what can be the value of potential at Q due to positive charge of the dipole? That is V1 equals KQ divided by R minus L, as distance of point Q from positive charge is distance R minus half length of the dipole, that is R minus L. Similarly, what can be the value of potential at Q due to negative charge of the dipole? That is V2 equals K minus Q divided by R plus L, as distance from the negative charge to point Q is this distance R plus half length of the dipole L. Then what can be the total potential at Q? The sum of the two potential due to positive charge of the dipole and potential due to negative charge of the dipole. So V total potential is equal to sum of potential V1 plus V2. Now you can see, if we take common KQ, the electrostatic constant, remaining 1 by R minus L minus 1 by R plus L, after taking LCM, this becomes R plus L minus R plus L divided by R square minus L square by formula A plus B into A minus B. So potential at point Q, V is equal to K 2QL divided by R square minus L square. As we know, 2Q into L is the dipole moment of the dipole. So potential at point Q can be written V equals K P divided by R square minus L square. If the dipole is an ideal dipole, its length L is very small as compared to R. In that condition, the potential at point Q is V equals K dipole moment P divided by R square. In this way, you can find value of the potential at a point on the axial position of the dipole. Now students, what can be the value of electric potential on the equatorial point of a dipole? So as you know, equatorial point of the dipole is lying on the perpendicular bisector of the dipole. Suppose this point Q is equatorial position or equatorial point of the dipole. So suppose point Q is lying at a distance of R from the center of the dipole, half length of the dipole is L. If we apply Pythagoras theorem, the distance of point Q from positive charge is square root of R square plus L square. Similarly, distance of point Q from negative charge is again square root of R square plus L square. Here you can see distance of point Q from both positive and negative charges is same, and potential due to a charge depends on two factors, that is amount of charge and the distance. So potential at point Q due to positive charge is V1 equals KQ by square root of R square minus L square, and potential at the same point due to negative charge is V2 equals K minus Q divided by square root of R square plus L square. This is square root of R square plus L square at both the places. What can be the total potential at Q? Sum of the potential due to positive charge and negative charge. As both the potentials are numerically equal due to their distance and magnitude of the charge, that is why potential due to positive charge V1 is equal to potential due to negative charge V2. That is why sum of the two potential at point Q is going to be 0. So at any equatorial point of a dipole, the potential is going to be 0. So students, what can be the value of the electrostatic potential at a point due to a continuous distribution of charge? If the charge is either distributed over length of a conductor uniformly, over a surface of a conductor, or over volume of a conductor. So in all the three cases, the linear charge density lambda equals dq, amount of charge on a small section of the conductor dq by dA, surface charge density sigma equals dq by ds, and volume charge density rho is equal to dq by dV. So what can be the value of potential at point Q if point Q has position vector r with respect to element of the conductor? So potential at point Q is V equals K electrostatic constant integral of lambda into dl divided by vector r. Similarly, magnitude of vector r. Similarly, potential due to this distribution K integral sigma ds, integration is to be done with respect to surface area of the conductor with its limits, and potential due to volume charge distribution, that is V is equal to K integral rho dV divided by magnitude of vector r. As electric potential has no direction, therefore all these quantities are going to be scalar at point Q. Students, in this part of the video, we are going to derive a very important relation of this chapter, relation between electric field and potential. Suppose there is a charge positive Q at point 2 O. First of all, we should know what is potential gradient. So here you can see, if this charge is placed here, there are going to be a potential and electric field existing in its nearby space. So as we move from point A to point B, the potential due to this positive charge going to increase. As we move closer to the charge, the potential increases. So potential gradient is rate at which electric potential changes with respect to distance is potential gradient. This is definition of the potential gradient. Means potential gradient can be written rate of change of the potential with respect to distance from the given charge. Means potential gradient is equal to dV by dr. And what going to be the relation between electric field and potential difference? So see, if there is a charge Q0, it's a test charge placed here at point A, the force experienced by the charge Q0 in the presence of this given charge positive Q is repulsive force. Direction of the repulsive force is away from the given charge, as both the charges being positive. So force experienced by charge Q0, F is equal to Q0 multiplied by E. Now suppose this charge Q0 is to be moved by distance dr from point A to point B. What can be the amount of work done in this process? Work done dW equals force multiplied by displacement dr cos theta. Value of theta is 180 degree, as direction of the displacement is opposite to direction of the force. We are moving the charge in this direction, that is why angle between displacement and the force is 180 degree. So cos 180 degree is -1, then work done is going to be dW equals minus Q0 E, that is force multiplied by displacement dr. This negative sign is for the cos 180 degree. Value of cos 180 is -1. Similarly, if we find the amount of work done to move the charge from A to B in terms of potential difference between the points, as we know, amount of work done to move unit positive charge from one point of the electric field to the other is defined as potential difference. So if potential difference VB minus VA is the amount of work done to move unit charge. Then what can be the work done to move Q naught charge? Q naught multiplied by potential difference. So work done to move Q naught charge from point A to point B can be written dW equals Q naught multiplied by dV. Here you can see both the equations, equation 1 and equation 2, they are providing same quantity, amount of work done to move charge Q naught from A to B in the electric field. So we can equate the amount of work done. So we can write minus Q naught into E into dr is equal to Q naught multiplied by dV. If Q naught cancels from both sides, then what can be the value of electric field? E is equal to negative of the potential gradient dV by dr. So in this way, what can be the relation between electric field and potential? The electric field is equal to minus potential gradient. This is the reason why sometimes we are getting unit of electric field as volt meter inverse. Volt is unit of potential difference, meter is unit of distance, that is dr. So unit of electric field as well as unit of potential gradient, both are similar.